So if you are somebody that wants educational resources on organic chemistry, Community is a good resource. I'll even show you guys where to find it. They popped up on my TikTok one day. It had a synthesis, and it said, how can I get from this starting material to this product? And obviously, being an organic chemistry professor, I was like, Grenier. But it was cool to see it come up. Community. I think this is their website, but if you search Community on TikTok, they come up with all these short little videos. I think one of the challenges of finding organic chemistry content on social media is it's not really well separated between OChem 1 and OChem 2. So you're going to see some things that you recognize and some things that feel very bizarre to you. And it's not always oriented the way that your professor teaches it. So you're going to see things that look familiar but really presented different. Yeah.
Like he has his very well, which I studied the other one where it's like the wavelength frequencies first. And 3000.
Yeah.
I did those before yesterday, and I was like, what is this yesterday?
Our textbook, the Francis Carey Organic Chemistry textbook, never highlights, well, we're going to talk about this today, but it never highlights the distinction between the sp2, sp3 CH bond and IR.
Oh,
It just says there are CH bonds in this range. That's it. Which is really strange because all of my training was like, look at this line at 3000. You can tell what type of carbon you have depending on where the absorption is. And that textbook doesn't teach it. We have another organic chemistry professor here who didn't use IR in his doctoral work, didn't use it in his postdoc work, didn't use it in his career. So when he started teaching IR for classes, he looked at the textbook. Textbook doesn't emphasize a distinction, and he doesn't teach it. And then his students show up in my lab, and they're like, what is this distinction you're talking to us about that our professor doesn't say? So we brought it up to him, and he's like, you want me to teach what's not in the textbook? That's not fair. Yeah, it is a different bond, and it absorbs different, and it's incredibly useful. So why don't we get into that? Yesterday we looked at mass spec, and we said that mass spec is useful for what? Yeah. Mass spec gives us the weight of a molecule, whether or not that's helpful. There are some really interesting things, like the molecular weight of a compound that has nitrogen is often an odd molecular weight. And if there's no nitrogen, it's often an even molecular weight, totally like randomly.
Can I ask one last question on that before we go to infrared?
100%.
So the input that goes into the spectrometer,
All those molecules.
do we know what we're putting in there first, or is it like an unknown sample?
Yes and no. So we have a GCMS on campus that our research groups use. So they know what compounds they're expecting to find. The gas chromatography component separates a mixture, and then the mass spec analyzes which molecule is coming out of that mixture first, and then we can use the spectrum as a fingerprint and say which compound it is. So sometimes you do know what compound, but you still use a database to confirm. Sometimes you don't know. Or maybe you're aiming to synthesize a compound and you're not sure you actually did. So you put it in there and it's kind of an unknown, and it confirms for you or gives you better information about what you actually did form. So there's a lot of different ways mass spec can be used. Same with IR. Sometimes you know exactly what you're looking for. I used IR when I was in graduate school to prove that an organic molecule was binding to a copper center in this material that I was trying to make. And by looking at where the frequency was in the absorption, I was able to show that the bond had changed because its absorptive character had changed. So in that way, I knew what I was looking for, and I looked for that difference. But other times, IR is useful when I have no idea what I have, or when I think I have something and I want to verify it. So IR, infrared spectrometry. This gives us bond types. Now I'm going to say that is approximately equal to, it's not exactly equal to, but it's approximately equal to functional groups. How did we define functional groups a few weeks ago? Yeah, an arrangement of atoms. Yes. So one component is that a functional group has a specific set of atoms bonded in a specific way, aka certain bond types, and they have characteristics that are common. So for instance, the carbon-oxygen-hydrogen bond is present in both alcohols and carboxylic acids, but the carbon-oxygen-hydrogen bond of an alcohol and a carboxylic acid do not have the same reactivity, they do not have the same characteristics, and a lot of that is due to the difference in the CO bond, CO double bond. So not all OH groups are alcohols. Some OH groups are carboxylic acids due to their difference in the bonding, the carbonyl is there, and their characteristics. So we can start to get functional groups out of this, but it's not always a perfect relationship. So I'm going to bring us back to our correlation table. Our correlation table in IR is going to be incredibly important. This is my correlation table. There are many like it. There are many different from it. But this one is mine. I built it for our class and also for the labs that we teach here. So there are some bond types that are not listed on this correlation table. There are some bond types here that you might not see on other correlation tables. For example, if you go to the Francis Carey textbook and you look at the correlation table that they give, you'll notice that this distinction here, two types of CH groups, one that's sp2, one that's sp3, not distinguished in the Francis Carey correlation table. And the name correlation, did I spell it wrong? I feel like there's an A after the E, but I can never remember. It's right? Oh, yeah, well, that's Word. That has, like, you know, spell check and stuff. I wouldn't give myself credit for that. Not to be redundant, but correlation tables correlate bond types to a signal on the IR spectrum. And there's actually a couple of things that we notice about the bond type. If you look at the very first row, we have the NH of an amine, which is actually maybe too generic. This should be amine and amide. But it says after it specifically stretching. So that means you take the nitrogen-hydrogen bond, you make that bond longer. And then like a spring, it compresses as well and it vibrates. And how do you get that bond to stretch? You need to give it energy. And how do you give that bond energy? You provide electromagnetic radiation. But not just any electromagnetic radiation, only the specific amount of energy that is required to make it stretch. So it absorbs within this region, depending on how else that nitrogen is bonded in the molecule. You might see it shift from side to side. And within that region, it has some characteristics. It doesn't absorb all of the light that hits it, but most to some of it, or some to a lot of it. Weak to medium intensity. And depending on how many NH bonds there are, different number of signals or peaks show up. But if you scroll down, and you look down here, 3 rows above this dark black line, you see NH again, but this time it's described as bending, meaning that the bond is no longer stretching back and forth, but the bond is actually compressing on itself side to side relative to the other things that the nitrogen is bonding to. And that motion takes a different amount of energy. So we look at a different frequency range, and we see that it absorbs not with 1 or 2 peaks, but always just 1, and it absorbs with a different intensity. This, it absorbs most, some to all of it, right? Medium to strong absorption. So different bond types also absorbing in different ways, looking at the different energies that are needed. One thing that I like to show is this energy diagram. So this is not our correlation table yet. This is bond length on the x-axis, and this is potential energy. I demonstrate this in general chemistry when we talk about why a bond is stable, why a bond forms and doesn't easily break. When 2 atoms are very far apart, you can essentially say that they're at net 0 energy. When 2 atoms start to get close, their energy drops off. And if they get too close, their energy skyrockets. You compress those 2 nuclei, the positively charged nuclei will repel each other. You pull them apart, the electrons will attract the nuclei back together. And then you get this vibration between these 2 bond lengths. And you can notice that in this curve, there are many different vibrations that can occur. You can vibrate a short distance, or you can vibrate a large distance. Not to get too complicated, but bonds have to absorb or behave according to certain rules. They have to follow laws of symmetry. So this is not a continuum. Bonds cannot bounce at any of these points, but bonds can bounce at any of these points. Discrete values. Excuse me. So the difference in energy, say from this more stable, shorter vibration to this higher energy vibration, that is the wavelength of light that we're looking for. Excuse me. H nu is often a way to abbreviate light. We are going to be looking at light with units of inverse centimeters when it comes to IR absorption. Inverse centimeters, is that frequency or wavelength? Frequency. Even though it is a unit of length, it's actually a unit of per length. And anytime you have a per something, you're looking at frequency. Per second is hertz, that's frequency. Per centimeters, frequency. This per centimeter is called a wave number. One more thing I want to say about bond types. We're not just analyzing the atom on either side of the bond, but we are analyzing, in some cases, the hybridization. CH is not a meaningful bond type to us. We need to distinguish an sp2CH from an spCH from an sp3CH. That is the bond type that we'll need to analyze. We're not just looking at OH, but we're looking at the OH of an alcohol or the OH of a carboxylic acid. Those are the bond types that we're looking for because they are different from each other. But you'll notice on the correlation table that not every bond type is unique enough from other bond types. There's this region here in the middle of the correlation table that has all of our carbonyls, all of the CO double bonds. Carbonyl is a bond type, but we're trying to be more specific about hybridization or functional group. But you'll notice that the CO bond of acid chlorides and anhydrides, they absorb in the same range. So I might be able to say, I know I have a CO double bond, and I know I have a CO double bond of one of these two groups, but I don't know which group it is. You can see that this range has a small overlap with the next set, carboxylic acids and esters. And carboxylic acids and esters had an overlap with the next set of ketones and aldehydes. And ketones and aldehydes have a small overlap with the next type, the CO double bond of the amide. So we can try to be more specific as much as possible, but it's not always possible to get down to the exact functional group. So bond type, sometimes proportional to the functional group. I also want to point out something about the sp3CH. We said that the alkane functional group is carbon-carbon single bonds with only hydrogens attached. You'll notice here that I am not calling it sp3CH alkane. That's because an sp3 hybridized alcohol might also have an sp3CH bond. It's technically not an alkane carbon, it's an alcohol carbon. So this word aliphatic, that's what we give to this sp3CH. Oops, I spelled that wrong. Aliphatic, maybe we can say it this way. All alkanes are aliphatic bonds, but not all aliphatic bonds are alkane bonds. If we just take a small molecule like isopropyl alcohol, rubbing alcohol, and we look at the CH bond here and the CH bond here, you might say that this CH bond is alkane because that carbon is only bonded to hydrogen and carbon. But this CH bond is not alkane because that carbon is bonded to an alcohol. So we'll use aliphatic to describe both of those bonds because they're both sp3CH. Sound good? Don't want you to feel confused by that word. It's not anything trippy. All right, just like mass spec, I want to give you guys what the spectrum looks like. Along our x-axis, we're going to have wave numbers, units of inverse centimeters, frequency, and this typically ranges from 4,000 wave numbers on the left to 400 wave numbers on the right. Can you tell me how frequency is changing from the left to the right? Aiden?
Energy gets lower on the right, and the amount of absorption is weaker.
Amount of absorption does not necessarily get weaker. Amount of absorption is relative to the bond that is absorbed.
That is true, yes.
But frequency is decreasing to the right, which means what about the energy of light? The energy of light is decreasing to the right. Tell me about the wavelength of the light as you move from left to right. Good. Increasing wavelength. Excuse me. Sorry? Wavelength and frequency are inversely proportional. Energy and wavelength are inversely proportional. Energy and frequency proportional to each other, directly proportional. I have some students that look at this and feel weirded out by it because they see a high number on the left-hand side and a low number on the right-hand side. I think maybe I've just been looking at them for too long to find it weird. But maybe you should think of it as increasing wavelength to the right, and that's why it's organized the way it is. I don't quite know why they chose to orient it this way and not reverse. It's just the way that it is. On the y-axis, we look at percent transmittance. What does that mean? Okay, our instrument, well, there are different ways that this instrument can be set up as well. Most instruments will shoot light out of a source. It goes up and it hits the sample. Some of that sample absorbs that light within a specific frequency, whatever relates to its bond. And again, not every bond absorbs light very well. Some do absorb it very well, some absorb it a little bit. The rest of that light gets reflected off of the sample, and it goes back into the instrument and hits a detector. So the detector recognizes how much light was put out and how much light is being received. And it looks at how much light is being transmitted, the opposite of what is being absorbed. So we're going to be looking at absorption peaks. Up here at 100% transmittance, that would be a baseline. That's to say, all of the light that the sample put out is absorbed, all of the light that the instrument put out hits the detector. 100% of it is transmitted, none of it is absorbed. What's interesting is that if you run an IR spectrometer with nothing on it, you do not see baseline. Instead, you see something like this. Yeah, I always do this badly. Do you see a straight line across the top? Oh, you see all of these dips. And I do want to direct your thinking about it. These are not peaks that come up from the bottom. These are actually dips, peaks that come down from the top. This is light that is not being absorbed. This is light being transmitted. And this is light that is being absorbed. This is light that is not being transmitted. So my background absorption looks something like this. And these we're going to call absorption peaks. I know some people like to call them or think of them as like an absorption valley because it's not a peak. But I think by definition, calling it an absorption peak against transmittance is actually correct. If this was, let's say, referred to as a transmittance peak, then I would say a peak indicates where light is being transmitted. Here's a transmittance peak. But I don't care about what light's being transmitted necessarily. I care about what light is being absorbed. So I'm looking at a downward peak. You guys comfortable with that? We don't get to make the rules, we just have to follow them. And that's background absorption. What is in the air that is absorbing this? This is if a sample has, you know, that says D-glucose. That's not, it does look pretty similar. It's not the one I'm looking for though. I mean, this is, I guess, a little bit closer to what I want, but oh yeah, see, I don't know how to use technology. I don't know how to open the image, so we're just gonna look at this.
Save it
No, I don't want to save it.
as.
Anyways, you can still kind of see there's a dip on the left, there's this sharp peak here. Regardless, this is background, literally air. And the question is, what is in the air that is absorbing in the IR? Photons don't absorb photons. Sorry. Huh? Actually, there is a rule that I didn't explain because I don't think it's super meaningful. The only bonds that absorb in the IR are bonds that cause a change in dipole moment when they stretch or when they bend. So you'll notice on the correlation table that there is no carbon-carbon single bond. That's because carbon-carbon single bonds just won't cause a change in dipole moment if they stretch. And because of that, they don't absorb. Water absorbs in the infrared because the OH bond causes a change in dipole moment. And the OH bond of water is very similar to the OH bond of an alcohol. We see that that absorbs in this high frequency range.
What about that single electron covalent bond?
I don't know if they've tested its IR absorptivity. We'd have to go and read their paper and see. If you look at this high frequency region, you can see that a lot of light is being absorbed. That's mostly from water. If you get too close to your infrared spectrometer and you breathe on it, you'll see this peak intensify. And then there's this other peak here and here, usually credited to carbon dioxide. Carbon dioxide is much like a carbonyl. It's got that CO double bond. And when carbon dioxide bends from linear to bent, it changes its dipole moment, so it absorbs very well. Methane, sp3ch. Methane absorbs incredibly well. There's not a lot of methane down here at surface level, but we are breathing a lot of water, and we're breathing a lot of CO2, and so there is a lot of absorption from those two things next to your spectrometer. Oxygen, O2, does not absorb in the IR. Nitrogen, N2, does not absorb in the IR. And I do want to make a point to the world, our planet, which is if we didn't have water in the atmosphere and carbon dioxide in the atmosphere, we would be a very cold planet. The water and the carbon dioxide and the methane in the air, they absorb the infrared light that the Earth is radiating off as it cools. It absorbs that light and it holds onto it as heat, as kinetic energy, and it gives us warmth. If all we had in the atmosphere was nitrogen and oxygen, all of that infrared light radiated off from the Earth would pass right through the atmosphere and would radiate into space. Our little blue planet would look like a hot spot in the IR. But instead, it's absorbed by our planet atmosphere. Keeps us warmer.
Yeah, with like a chloroplast, absorb it the same way. Like, is this like one of those things that's just like the averages, or is it like it's dependent on what absorbs it?
A chloroplast,
Right.
like chlorophyll or carotene.
Yeah.
So let's look at a molecule. Chlorophyll. Oh, look at that. It gave me the absorption spectrum. Oh, that's its UV vis absorption spectrum, though. I just want to look at the structure. If we look at this, we can analyze a lot of bond types. There's a lot of CH bonds, sp3CH. There's some sp2CH. There's some CC double bonds. There's some CO double bonds. There's some CO single bonds. I think that's it. sp3CH, sp2CH, CH double bond, CO double bond, CO single bond, and then here there's the CN double bond. All of those bonds absorb in the infrared. But it's actually more interesting, the electrons here in that cyclic structure, the conjugated cyclic structure, they absorb in the visible spectrum. That absorbs red light, and it enhances the reflection of green light. So your chlorophylls look really green because they're absorbing really well in the red. They do absorb in the infrared, but not for the same reasons. And if you look here on their absorption spectra, you can see they absorb really well in the red. I guess they also do absorb in the blue and violet. But that's why they enhance the color green. Did that answer your question?
Yeah. I saw that magnesium. I was like, I forgot about that. Would that be right? If it could be red, isn't magnesium like that red pepper gives off that color?
Yes and no. It's the magnesium bonded to the organic molecules. It's the magnesium bonded to the nitrogen that causes it to absorb in the red. And if a plant, takes the magnesium out of its chlorophylls, pulls it back into its branches or into its trunk, it's no longer going to absorb the same color. And this is one of the main reasons that leaves change colors in the fall, because the magnesium is being sucked out. That's an important nutrient. A tree does not want to have to harvest magnesium every year. So towards fall, leaves will have their magnesium sucked out of them, stored in the branches. And that changes the absorption because the magnesium is now no longer a part of it. Color changes. Back to the IR though, not the visible. Okay, so there's a few ways that we want to analyze this, and just to make it clear, this correlation table is organized from high frequency to low frequency. Not all correlation tables are. You can find other correlation tables that are organized by functional group or bond type. And in that case, the frequencies are all over the place. But let's start there with absorption frequencies. First, there is an important spot at 1500 wave numbers. On the right-hand side of 1500 wave numbers, we give the name fingerprint. In this region, a lot of different bonds absorb, making it challenging to identify what bond is responsible for what absorption. some bonds only absorb in the fingerprint, which means those bonds are really hard to tell because you don't know if it's from that bond or from the plethora of bonds that absorb there. If you look at my correlation table, you'll notice this sharp black line that helps to distinguish groups that only absorb in the fingerprint region from groups that do not absorb in the fingerprint region only. It's really easy to take these three columns beneath my black line and say, if I have absorption beneath 1500, it's going to be this, or that. That's not what I'm trying to say. I just didn't want to take up a second page for my correlation table to show all of the other bonds that also absorb down here. Because all of those other bonds also absorb in the other region. These are the bonds that only absorb in this 1500 region. So finding them is a challenge. That's why it's a black line. These are the most challenging to find. I had an OChem 2 lab student. Every week they analyzed their product with IR, and every week in their lab report they said, my product has carbon-halogen bonds because I see absorption in that low frequency region. And I said, why does your product have carbon-halogen bonds when none of the reagents involved halogens at all? They said, I saw it on the correlation table and I thought that was it. So, trying to make it clear, these three only absorb in the fingerprint. Many other things also absorb in the fingerprint, making these three the hardest to find. The other region we call the functional region or the functional group region. Here it's easier to assign, but I'm not going to say that it is always perfect. I also want to take you to a specific division at 3000 wave numbers. I showed you guys that some bond types cannot be distinguished based on where they absorb, but some can, very luckily. To the north of 3000 wave numbers, we see the absorption of sp2ch bonds, and to the south of 3000 wave numbers, we see the absorption of sp3ch bonds. If we look more at the correlation table at this region, we'll see that it's not that their absorption range stretch very far. sp2 absorption ranges from 3150 to 3000, and sp3 absorption range from 3000 to 2800 or 2850, depending on where you look. So there is this really nice line at 3000. Neither of those bonds will absorb at 3000, but they will absorb just on either side of it. And that's really important for organic chemistry because it tells us, do I have anything aliphatic? Do I have any sp3 carbons? Do I have any alkenes? Do I have any aromatic rings? Anything that is sp2ch? So this is a really important distinction, but to clarify, your textbook doesn't highlight it. So I expect you guys to see it. If you go reference the physical textbook, they won't highlight it. I think that free online textbook that's linked as a resource, I think they do actually highlight the distinction. Okay, how are you feeling so far?
When you're like looking at these, are you always having to compare it to the background?
No, your instrument,
Negates all.
yeah, your instrument takes a background spectrum and then subtracts that from your analysis. Mm-hmm.
Susan can never see anything at the 3,000.
You're going to see stuff that butts right up to 3,000.
But it'll still go.
Mm-hmm. So when I give you IR spectra, I give you two lines on the spectrum. I give you a dotted line at 3,000, and I give you a dotted line at 1,500. And that is meant to be a reference point for you guys. You do not need to analyze bond types below 1,500, and you do. It helps you distinguish between the sp2 and the sp3 bond types at 3,000. So all of the IR spectra that I will give you will have those lines. Active is not as nice. Active does not necessarily give you those lines. Also, I am only giving you guys experimental data. Active gives you cleaned up data. So when I give you data, it's from SDBS. And SDBS is uploaded experimental data. I don't know where Active sources their spectra from, but their spectra are a little bit cleaner. Here's the IR absorption spectrum for the thing that we looked at yesterday, benzyl bromide. Here's 3,000, and if you follow this line up, it's so close, right? Especially those of you who are seeing this type of spectrum for the first time, I doubt that you would look at this selection of peaks and say, those come from different bonds, or even say that they are separate sets of peaks. You can see that they're kind of connected here. But 3,000 runs right up this crack and separates this one signal from these other signals, this one peak from that set of peaks. So a line at 3,000 tells us that I have both sp3 and sp2ch. The other thing that I want to say about absorption frequencies. Sometimes similar bonds absorb very distinctly, sometimes similar bonds overlap. We've already hit this a little bit. I'll just give you this comparison. The OH bond of an alcohol absorbs between 34,000 and 3,200 wave numbers. And the OH of a carboxylic acid, Ca, absorbs between 3,200 and 2,800 wave numbers. It's a similar bond, not the same functional group, but they're both OH bonds. And they show up in different frequencies. But then we've got the CO double bond of the ketone and the CO double bond of the aldehyde. And these absorb both between 1740, 1660. Similar bonds, not the same functional group, but their absorption range is basically identical. Lastly, I hate saying this, you've got to be okay with some hand waviness when you analyze these spectra. These absorption frequencies are general ranges. They're not hard fast. They're not set in stone. Maybe an exception to that is this division at 3,000 wave numbers. That is hard fast. I've yet to see one of these bonds cross that line. But when your correlation table says the CO double bond of an aldehyde or ketone will fall nicely in this cute little range, that's not always true. Sometimes they can absorb at a higher frequency, sometimes they can absorb at a lower frequency. That can make it really challenging because remember, there's already an overlap between the CO double bonds of the aldehyde and ketone and the CO double bond of the ester and carboxylic acid. So if the CO double bond of a carboxylic acid drops even lower than 1715, it's really going to look like it's a ketone or an aldehyde. So you have to be able to say, that range isn't exactly where I would expect, but these ranges are allowed to move based on how the bond is surrounded by other bonds. What else is happening in the molecule? That's going to impact the energy of the absorption as well. These are good approximations. They're not hard fast. Are you guys comfortable with that? All right. Then what I would like you guys to do, just quickly, looking with absorption frequency, I want you guys to see if you can find the CC double bond on this spectrum for the aromatic ring. Remember that what we're looking at here is benzyl bromide. I want you guys to see if you can find the CC double bond. And while you're at it, maybe you can look for this, the aromatic overtones caused by aromatic rings, usually several signals very weak in intensity. Use the correlation table to help you analyze this region of the spectrum. Anybody feel like they found it? No?
Question.
Yeah.
So, some atoms, some bonds higher up will have a peak over like the 3000s.
Yeah.
And a bunch of peaks in the Theta region. Will these ones that only have peaks in the Theta region only have one peak?
No, not necessarily.
Or will it have peaks underneath below it? Like the same way it usually has peaks below it?
I'm not sure I understand.
Like, would a nitro group have peaks below its range?
Give or take, my OChem 2 labs just did a nitration reaction the other day, and they found their two signals, but it was more like 1325 and 1555. Those were the frequencies. So that's kind of the hand waviness. It's not going to be exactly at 1550 and 1350, but it'll be close to it.
But will you see more peaks down in like the below 1000 range? With like the other,
No, not for the nitro group. Those are the two absorptions for the nitro.
it'll be only the.
Mm-hmm. Yeah. Oh, yes. Yeah, you want to... Maddie, you got a question or you want to solve it?
Question.
Okay, let's hear it.
When it says the like weak, medium, strong, is that like the depth of the?
Yep.
Okay.
I'll look at that one next. The shape and the number of peaks. Someone else have a question? Okay. You want to tell me where the CC double bond is? Or show me?
The light.
Or the aromatic overtones?
Okay, so I found
are, 'cause
Yes.
they're weak
Yes,
and they're multiple.
that's right.
And then that is like, it's kind of little thing.
Yes.
It also lines up with.
Exactly. Perfect. Well done. So you guys will see a dotted line when I give this to you that runs at 1500. And you can see like there looks to be very intense signals down here. We're not even going to try and assign them. In this molecule, they're likely CH absorptions, but we're not going to try and assign them because they don't tell us enough. We're going to stick to the functional group region. Correlation table tells me that the CC of the aromatic ring usually absorbs right at 1600. So I'm going to take this line at 1600 and bring it straight up. There's my absorption. Now it looks like there's two peaks. Don't know what to tell you. Either one of them is the absorption or both of them are. But we had enough confirmation that there is CC double bond of the aromatic ring. And the overtones, which is just a fancy way of saying resonance absorption, those show up here, 19 to 1700. And if I bring that straight up, I see these several weak absorptions giving me evidence of my overtones, my aromatic overtones.
Will those two peaks at 1500 be the nitro?
No. Mm-mm. Well, first of all, the nitro would absorb at 1550, and there's not really anything there. But this molecule, benzyl bromide, does not have a nitro group. So if I saw absorption at 1550 and 1350, something else is causing it. Notice how this molecule, benzyl bromide, does not have a nitro and oxygen, but it does have a halogen. So if I look in that fingerprint region a little bit more, the halogen is expected to absorb between 850 and 550. Okay, here's 850, and here's 550. These three peaks are probably the CBr bond. But that's really hard to know because they're just about as intense as these other bonds. And it's not like they're the only thing that's absorbing down here. So hard to analyze, not super easy to come across. But we call it a fingerprint for a reason. I could take an experimental sample of this molecule and a literature sample, this, SDBS. And I could match up those spectra to each other, and if the absorption has the same number of peaks, at the same wave numbers, with the same intensity, they're a match. This acts as a fingerprint to the molecule, very similar to how mass spec acts as a fingerprint to the molecule.
Will we have access to this table during tests?
Yes. So first of all, I want you guys to download this and use it while you do your unit test for Unit 3. Actually, I'll show you what it looks like. It does look a little bit different on the exams. All that I modify when I give you the exam is the left-hand column. So if you scroll down, the first page are the useful correlation tables. I don't put the mass spec correlation table on here because I just don't find the mass spec correlation table to be worth the space. The NMR correlation table is a little manipulated as well. When I show it to you guys, there will be names here for the functional groups. And the IR correlation table is a little bit different. When I show it to you guys, it has a description, a picture of the bond type. Here it's just a name of the bond type. You guys okay with that? You still get them, but they're like a little bit less information given with them. If you want to, maybe you print off this page from the midterm exam and the final exam, and you study using this correlation table, seeing as how that's the tool you'll have on your exams. I do not want you guys to memorize any of this. I want you to know how to use the correlation table as a tool.
On the other chart, the aromatic overtones aromatic ring looked really, but I guess I don't really know.
What is the difference?
I think one was like 1600 and then one was like a range, but.
Are you thinking of the CC
Yeah, so like
the CC double bond of the alkene and the CC double bond of the aromatic ring?
Well, that as well, but like, okay, aromatic overtones is 1900 to 1700, but then for below it,
Just
like just the
the
C.
CC double bond.
Okay. Just the CC double bond in the aromatic ring.
Yeah.
Is a CC.
That's right.
And then a CC double bond in a ring or otherwise.
Of an alkene.
Of an alkene.
Remember that
Oh,
alkenes
okay,
are
alkene.
not aromatic rings.
Okay.
I could have given that here as well.
Yeah.
I compared that OH is the same, but they're different functional groups. CC is the same, but they're different functional groups.
Yeah.
Except that these actually have more in common.
Yeah.
Aromatic rings are almost always right near 1600. Alkenes have a larger range that they absorb in, including 1600. So if a molecule has both an aromatic ring and an alkene, it can be challenging to know which or both you have. And if you notice up top, the sp2ch for both of them overlaps quite a bit. So even though the alkene and the aromatic ring are different functional groups, even though the aromatic ring does not have alkenes, their absorption is a lot more similar.
Wait, what's the distinction between medium and strong curve? Is it like 30% range?
We'll get into that next. Any other questions on the absorption range? You guys see how we can look at the correlation table to find where on the spectrum a bond should absorb, and then go to that spectrum and look at that range and see the absorption. You guys also noticed how if we look back at the whole structure, the aromatic overtones, the CC double bond, very small signals. A lot of other signals, very loud, and we're not even analyzing all of them. And then also some other small things that we're not going to analyze. So that's where some more of this hand waviness comes into. I get to kind of pick and choose which signals I want to interpret. If I see a signal that makes me think, do I have a nitro group, but I know my chemical formula? No, I don't have a nitro group. I'm just not going to interpret it that way. So the next thing, moving away from absorption frequencies, the next thing that I want to look at with you guys is the number and shape of peaks. There's a lot of different cases, so it can be hard to summarize it. I'm going to do my best to. Most bonds have one nice absorption peak. Some bonds have a set of peaks that are all close together. And then other bonds have always a specific number of peaks, sometimes depending on the number of bonds. So the number of peaks really varies. The NH bond is the only bond that changes the number of peaks you see based on how many of those bonds are present. If there is only one NH in a molecule, you'll see one peak. But if there are two NHs in a molecule, you'll see two peaks. When you look at the CH of the aldehyde and the nitro group, the CH of the aldehyde always has two peaks at specific frequencies. Again, with some hand waviness, plus or minus a few wave numbers. I like to call these twin peaks. One at 2800, one at 2700, give or take. Always two, always the same intensity. Always at those values, give or take. The nitro as well. Two peaks, equal in intensity, 1500 and 1350 wave numbers. Those are the only ones that are consistently the same. Most of the other bonds are going to show up as, there is one other one that's usually two. The anhydride having two different CO double bonds. The anhydride often has two peaks, but that one's a lot messier and a lot less common, so I don't want to look at it too much. Most other signals have just one absorption, but then we see the sp2 and the sp3ch. And these ones really vary. Oftentimes, it's several peaks. It is not dependent on the number of the bonds, though. And this really trips people up. They think benzyl bromide has two CH bonds. Maybe I should see two peaks. But we noticed in the spectrum, we actually only see one peak for that sp3 CH bond. And then the aromatic ring has five. Maybe I should see five peaks, but we see actually just three. So there's no correlation here. It's often several, but it's often inconsistent. What it will do instead, it's just analyze them as a group. Whether it's 1, 2, 3, all of them get analyzed as just one group that say the same thing. sp2ch, sp3ch.
Are we only counting the downward inflections as peaks?
Yes.
And the upwards are just space in between?
Yes, that's right. So you really do have to get familiar with how you read it. I don't want you to read it from the bottom up. You should read it from the top down. Yep. When I say analyze as a group, what I'm trying to say is you don't need to look at this spectrum and say 3090, 3050, and 3025 wave numbers. sp2ch, sp2ch, sp2ch. That is too much. But you can say peaks from 3100 to 3000, sp2ch. They all get analyzed as one group. Does that feel okay with you guys? Now that's the number, but the shape comes in two flavors. You'll notice on the correlation table that most peaks are listed here as sharp. And by sharp, that means it leaves baseline and then it comes up to baseline, even if it does that several times. Sharp peaks. The OH of an alcohol is very broad. Actually, that one is a bit too broad for my liking. You can see that the OH peak kind of rounds out at the bottom, takes up a much wider range. And the OH of the carboxylic acid very broad, meaning when this one leaves, it doesn't come back. I put a few squiggles on there too because they are often littered with sharp, jagged pieces. So I want to give you guys a comparison quick. Here is the absorption, IR absorption spectrum for benzoic acid. Actually, I might not have done a good enough job putting the ziggy-zaggies in there. Look at this. Starts to absorb, doesn't stop absorbing until it gets down towards 2,500 in this case. Very broad absorption, and it's got some weird gunk going on. It's got weird stuff. And if you look at where that region is, that's 25, 26, 27. Nothing else absorbs there. So that's not a signal from any other type of bond. That is the signal from the carboxylic acid. It just looks really jagged. Okay, keep that in mind. Unfortunately, STBS doesn't like when I have multiple tabs open.
So do we just read the lowest point?
Yeah, you would say that the lowest point on the absorption is like the center of the absorption peak. But you could say it's a range. You could say the OH of the carboxylic acid absorbs from this to this. Look at the absorption spectrum of benzyl alcohol. Do you see how much cleaner that absorption is? It's broad still. Compare it to the sp3ch sharp, sp2ch sharp. The OH here is broad. So first of all, they absorb in a different range, and they absorb with different widths. And then bringing us back to our correlation table, that's clarified in there. OH of the alcohol, broad. OH of the carboxylic acid, very broad. Benzyl alcohol, it has a CO bond, and the CO bond absorbs somewhere between 1,000 and 1,300, and it absorbs strongly, which means it's probably this, but that's really hard to ascertain. Then we have weak, medium, and strong peaks. This refers to the intensity. How deep does it go? Here's one of the worst parts about this. It's always relative. It's relative to the strongest absorption. You You have a bond that absorbs strongly. Everything else will look medium to weak. You have a bond that absorbs medium. That's going to appear the strongest, and the weak are going to appear medium. You have something that only absorbs weak. They're all going to look medium to strong. Here is the IR absorption spectrum for just benzene. If we look at our correlation table, we expect the sp2ch to be weak to medium and the CC double bond to be weak to medium. And this looks a little bit more like strong. This comes down quite a ways. I wouldn't necessarily say it looks medium intensity. Maybe this looks medium intensity. And this, at 1600, shifted a bit. Still weak. It's all very relative, which is one of the worst things. But something nice. Carbonyls, CO double bonds. They always absorb strongly. So when you have a CO double bond, it can be very beneficial to just start there. Look for a CO double bond. Shows up in a specific range, 18 to 1700s range. Everything else in comparison is going to look smaller. So let's do a comparison. Let's say here the sp2ch of the aromatic ring, it looks like it's coming almost 75% of the way down the transmittance. Let's change this and look at benzaldehyde. Benzaldehyde has the same ring, but also a CO double bond. The CO double bond is a strong absorber, and relative to that, the sp2ch looks weak. It's terrible. Now, actually, one of the issues here is that people that take these, or the instruments that take this spectrum, are kind of manipulating the data so that it's all relative to itself. I know that it says percent transmittance, but it's similar to mass spec where you've got relative intensity, which is just normalized to the tallest peak. It's something similar here. It's not necessarily always the same intensity. It's made relative to the sample. Did that help answer questions that you guys had on the shape, the intensity, and also the placement? Yeah? Okay. Then there's one last thing that I want to cover with IR in terms of how it helps us narrow down functional groups. And that's what I like to call corresponding peaks. I could be wrong, but I think that I'm not trying to sound weird. I think that I came up with this description, so if you look this up, you might not find resources on it. But it's just my way of tackling the analysis of an IR spectrum. I think it makes most sense for us to look at corresponding peaks with the correlation table present. The idea here is that some functional groups have multiple expected IR peaks. If I suspect a certain functional group is present, I should be able to identify all of its IR peaks. If any of its IR peaks are missing, something is probably wrong. Let's look at the aldehyde. One of the most prominent peaks that you'll find from an aldehyde is the CO double bond. For instance, here we've got a CO double bond that is pretty much centered right at 1700. Thank you, Cam. I think I should unlock it. Now, thinking back to the correlation table, a signal at 1700, can we really be confident that that is the result of an aldehyde? These two carbonyls, they don't absorb all the way down to 1700. These two carbonyls, they don't quite absorb all the way down to 1700. This last carbonyl, the amide, doesn't quite absorb all the way up to 1700. But that leaves me guessing whether I've got a ketone or an aldehyde. A ketone has no other corresponding peaks. If you look through the correlation table, ketone shows up in one place. Right there, the CO double bond. But the aldehyde shows up in two places. If I have this signal and it truly belongs to an aldehyde, then I should also see the CH bond of the aldehyde. My correlation table tells me the CH bond of the aldehyde is twin peaks, 2800 and 2700 wave numbers. Do we see that? Here's 28, here's 27. Twin peaks, aldehyde. What I've just done is used the CH of the aldehyde to confirm that the CO double bond belongs to an aldehyde. Confirms that the CO double bond is not a ketone. What do you guys think? All right, I'm going to put up an example. I'm not going to let you know what it is. Yeah, it's all right. Oops. And what I want to point out on this spectrum right away is that there is a CO double bond at about 1700. Oh, not 1700, 1710 is actually a little bit more appropriate. What functional group does that carbonyl belong to? Let's look at the correlation table. And we look at this range near 1710. That's in a pretty close proximity to esters and carboxylic acids, but it also is within the range for ketones and aldehydes. Aldehydes have a corresponding peak, 28 and 2700, but I see no twin peaks here at 28 and 2700. Ketones have no other corresponding peak. If it's an acid, what corresponding peak would you expect to find? Yes. If it's a carboxylic acid, I should see a very broad absorption from 28, 30, 32 to 2800, 33 to 2800. What if it's an ester? If it's an ester, would I have a corresponding peak? We can do this control find here. Ester shows up 4 times. No, that's because it's down here as well. No. I don't know why it says ester shows up 4 times. I'm seeing it twice. If it's an ester, I would have a corresponding peak down here in my fingerprint region. But when I look back at my structure, I do see the very broad absorption of the carboxylic acid. So because I have OH broad, here the range looks like it's from maybe 3,400 down to 28. Together, these confirm what my carbonyl is, a carboxylic acid. If you think you spot the bond from a functional group, go look for everywhere else that functional group shows up on the correlation table, and go find all of its other signals. The aromatic ring has sp2ch and cc double bond. Same with the alkene. The amine has a bending down here by 1650 and a stretching up here by 3600. Go find both of them. If you think you have one, you should be able to find the other. If you have the CC triple bond of an alkyne, you should also find the CH of an alkyne, SPCH. There's a lot of information, but it's basically a puzzle. You get snapshots of what's in the molecule. In no way can you predict what the molecule is, or how it's attached, what its structure is, but you start to learn about bond types, which can give you some information about functional groups. All right, so I want to look up one more molecule for you guys, and in the last 7 minutes, what I would like for you to do is try to identify all of the bond types using a correlation table all of the bond types that are present in the compound. And remember, experimental spectra are messy sometimes, so you've got to be able to give some hand waviness to it. Feel free to work together, by the way, especially if not all of you have a correlation table pulled up. Work together, point things out to each other, see how many peaks above 1500 you can assign to their bond type.
question with broad versus sharp, is it how quickly it returns up to baseline or how sharp the bottom of the peak is?
That's a great question.
Or some combination thereof?
Generally, it's how sharp the bottom of the peak is. Like if you were doing math, like the slope of the sides too.
So if you potentially have a sharp bottom that overlaps with it.
Yeah, you're looking at that peak on the left and you're a little confused by it, right?
Both.
I agree. Yeah, or hold some of it as like, I am not sure exactly what this tells me. Maybe it's this, maybe it's that. And if we can't prove it, then that's what we have. IR is not foolproof. IR can leave you with some questions still. So remember, like the carboxylic acid OH, we call it very broad, but it also has these really sharp pieces to it. So it's a little bit of both, I guess. It's hard to narrow down. All right, you guys have looked at it long enough alone. I want you guys to start talking with each other and seeing what you have found above 1500.
Oh, okay. So, I agree with you.
Right after 3,000, just underneath it, the lowest peak.
Over time. Yeah.
CHSP3. And then right at 1600. That would be the aromatic ring
Yes. I'm just.
You guys feel confident on anything?
Define confidence.
Do you have any that you
I
you really don't doubt, and some that maybe you have?
have 4 options.
Okay.
The first one is a possible amine, right at just past 3,600.
Okay.
The next one is an aliphatic, right below the 3,000, because that's in a range of 3,000 to 2,800. Right there.
Alpine.
What about these?
Alpine, and then, I don't know if there's no.
Remember, this is a really nice line. If you're looking both left and right of it.
Oh, to me, I'm not seeing it wrong.
Carboxylic
Because it looks
acid.
very like this going down.
Carboxylic acid is too broad. Carboxylic acid is so like this.
Yeah.
Oh,
Right
okay.
on it, right at
Yeah.
comes down to and stops.
Aromatic ring or an alpha.
The sp2CH.
So how do you
Somebody's in
know
the way.
either one?
You don't. Yeah, that is a challenging part. Now, I don't see anything at 1550 to suggest the nitro. And then when I come down to 1350, I'm not seeing a sharp peak. And the nitro is expected to be sharp or strong, at both of them. So I'm thinking maybe not nitro.
At 1,600.
And if there's the amine, if this is the NH stretching, I should be able to see the NH bending somewhere in here. And if it either it's overlapped with your aromatic ring or this isn't an aromatic ring.
What do you mean bending your strength?
The NH absorbs in two different ways. The NH bond absorbs by stretching. The NH bond also absorbs by bending.
How would you know it was
It absorbs in different frequencies according to the correlation table. You'll see NH in two places. Once at the top, once closer to the fingerprint. Okay guys, we're out of time, so tell me what you found. What do you feel most confident on being present here?
Aromatic.
Nope, that's not a bond type.
Oh.
Give me your
sorry.
bond type, sorry.
CC of the aromatic.
CC double bond, tell me where you found it.
1600.
Okay. Now, aromatic ring's not the only thing that absorbs that 1600. Other things, 1600 is within the range, like the NH of an amine.
It's also got the overtones. as
Good.
well.
Aromatic overtones are there. Now, sticking on this idea of corresponding peaks, the aromatic overtones are not always present, but they are a great resource if they're there. There's also another bond that corresponds to the aromatic ring. We've got the CC, double bond. Well, yeah, there's that overlap. But there is another bond type that corresponds to being an aromatic ring. What other bond type? The sp2ch bond. Do we have that? Because then some of these might need to get canceled. Do we have that there?
Yeah, right on that.
Here's 3000. Just to the left of that, I've got sp2ch. What else do you guys feel confident is here? sp3ch. Just to the right of 3000. What else? There's one left, and I suspect this is the most challenging.
And oh, stretch.
It looks like, no, there's no NO nitro group. If there was a nitro group, there would be a strong absorption at 1550, and there's nothing there,
Oh,
and a strong absorption at 1350.
oh.
Now, I would say it's between NH and OH. This is much broader than most NH groups that you would see, but I agree it's not broad at the bottom. For some reason, it came out sharp at the bottom, but it is overall broad. If that was an NH absorption, I would expect another NH absorption here, but I actually feel pretty confident I have an aromatic ring from all of these corresponding peaks. So I don't think that's NH up top. I think that's OH, specifically of an alcohol, and it is in a high range. It looks like it's around 35, 50 wave numbers. That's higher than what our correlation table tells us to expect. Do you know the molecule now? No, you can't possibly know the molecule from its functional groups. We know that it has an aromatic ring. We know that it has an alcohol. And we know that it has sp3ch carbons. I gave you guys propofol. Again, that's what we did at the end of class yesterday. But you would have never known. You don't have its molecular mass. You don't know if that aliphatic CH is from alkane or just something that has an sp3ch. You wouldn't know that there are two of them. And it's even hard to know that it's an alcohol.
I hope this doesn't sound like I'm trying to be a smartass, but what does this realistically accomplish? Like
It tells us what functional groups are in it.
but it doesn't tell us what it is.
That's true.
Just the functional group.
That's right.
It doesn't function group.
So come back next week where we'll learn about NMR and learn how to build structure from NMR data.
There you go. But doesn't the functional group kind of tell us something about the reaction?
Functional group will tell us about reactivity. If we did a reaction, it would tell us whether we did it right or not. But that's about it. Have a good weekend, guys.